like tradition, I'm actually going to start on time. So we're very happy to have Soumi Nandi with us from Bangalore, where she is a research assistant working with Jaipur. Before this, she was a PhD student at ISAC Kolkata with Arijit Ghosh, who was also linear, and Saurabh Chakravarti, who I planted at some point.
He has also been
Yeah. Oh, he's also linear. Okay. So now we have the actual person doing it. You can start.
So, good afternoon. Today I am going to present our results on covering surface of the hypercube with polynomials and hyperplanes. This is a joint work with Arijit Ghosh, Chandrima Koyal, and S. Venkatesh. This is a brief outline of my today's talk. So, let us first start with the problem statement. So, suppose in 3D we are given a die and we want to cover all its corner points using planes. So, what will be the minimum number of planes? Any two parallel planes that cover two opposite faces is sufficient. Similarly, if in any dimension n we are given this hypercube 0, 1 to the power n, and we want to cover all its vertices using minimum number of hyperplanes, then any two hyperplanes that covers two opposite faces are sufficient. Namely, some xi equal to 0 and xi equal to 1 are sufficient. But now, suppose we ask the question with a slight twist. Instead of covering all the corner points, now we want to cover all the corner points except one. So, suppose we have this hypercube and we want to keep that origin, that is all 0, as uncovered and cover all the other vertices with hypercube. So if we take xi equal to 1 for all I running from 1 to n, then that n hyperplanes are sufficient, right? But now the question is, can we do better?
I think you said earlier that in order to cover all corners, two are sufficient.
Yes.
When you remove one corner,
Yes.
you should still be sufficient, right?
No.
Or you necessarily have to not
Necessarily.
touch it.
So I want that
You have to do
vertex
it
as
necessarily.
uncovered and all the other points as fixed. So this gives us the famous result by Alon and Fiiedi, and they showed that this in hyperplanes will be necessary also. That is, if we want to cover all the vertices of the n-dimensional hypercube, leaving only one vertex as uncovered, then we will require at least n hyperplanes. So, and also this in this family of n hyperplanes that does this covering job, that is not unique. So one is that xi equal to 1, where I runs from 1 to n. And also, if we consider this family where summation xi is k and k runs from 1 to n, then this family also do the same job.
Sorry, what was that number?
Sorry.
What did you say about the second thing?
So the second thing is, it is just I'm taking summation xi.
So they will also cover all the points except the origin.
So
Family of n hyperplane.
basically,
Yeah.
how many ones are in?
Give two examples of cover.
Yes. Now observe that every hyperplane can be interpreted as a polynomial, as a linear polynomial. Now suppose instead of covering with every hyperplane is a linear polynomial. So
But there's an inequality.
no.
Yeah, sure.
So if we just the family of hyperplanes that does the covering, and I just take the product of all those hyperplanes, then that polynomial will be will cover all the vertices. That means the polynomial has 0 at every corner except the all 0. So hyperplane covering. Okay, so let me define this polynomial covering first. So we are interested in finding a minimum degree polynomial whose coefficients are coming from the real field, such that the polynomial vanishes at every point of the hypercube except the all zero. And at all zero, the polynomial does not at all vanish. Then we want to know what will be the minimum degree of such polynomials. So, what is the difference between this polynomial cover and hyperplane cover? So, a hyperplane cover is already a polynomial cover, but the polynomial cover need not be a hyperplane cover, because it might be possible that we get a low degree polynomial which does the covering job, but the polynomial cannot be factorized into linear factors over R. So, a polynomial covering will give a lower bound for the hyperplane covering.
You mean a degree lower bound of the polynomial covering needed will be a lower bound of the number of vectors?
Yes. And so, we have seen that in hyperplanes are equal, but for covering all the vertices of the hypercube except the origin and keeping that origin as uncovered. So the question is, if we just consider polynomial cover instead of hyperplane cover, then can we do it with low degree polynomials? Alon and Fiiedi showed that that is not possible. Even for polynomial covers, we will need at least n degree polynomials to cover all the vertices of the hypercube except the origin and to keep that origin as unknown.
So this time, the requirement for a polynomial is that it should not vanish on any of the coordinates and it should vanish on the.
No, just opposite. So a covering means it vanishes at that point.
And you don't care about what happens in the rest of the.
So
Rest of
I
the,
mean,
Other points.
so covering and uncovering means hyperplane covers the point means that point lies on that hyperplane. So when
One is a continuous, right? So how do you actually guarantee this is exactly zero? And then any point close to it.
No, but close here
You
is
will
not distance one, right?
But how do you define polynomial?
Oh, so here when she means the hypercube, it's only the corners.
So there's nothing
No.
contained inside.
No, there's two to the end.
But and also these polynomials are multilinear because she's only interested in the behavior over the hypercube.
Yeah.
So you can scale this polynomial and assume the place that it doesn't come, it doesn't vanish, it has value 1. Yeah, and then it's exactly the AND function.
You
Yeah.
can uniformly scale it, no?
Huh?
Yeah.
You can't uniformly scale it.
Why? Because it's vanishing everywhere.
you can still.
Oh, yeah, because it's on your, the.
So that's the
Yeah, you can have to.
well-known degree lower bound for the AND.
Yeah, yeah.
This is exactly.
Because you're interested only in the behavior of the polynomial over the Boolean hypercube, that's very important.
That's not important for scaling.
No, I'm saying by scaling you will alter its behavior at every other point, but it doesn't matter. Only the points of the cube matter.
Why? So you can, doesn't matter if it's defined on the cube or not, if it's zero at all vertices or.
What would you scale it with? You would scale it by its evaluation at this all 0 points.
Yes,
right?
1 over that.
Yeah, so I'm just saying that if it, anyway, we're seeing the same thing.
Okay.
So the next question is that instead of forbidding on a single point, if we want to forbid on a subset of the hyper, then what will happen? So formally the question is, suppose we are given a subset of the hypercube 0, 1 to the power n S, and S has more than one points. And we are interested in finding the minimum number of hyperplanes that covers exactly the points outside S, and none of the points in S is covered. Similarly, we want to know what will be the minimum degree of the polynomial that vanishes every other points on the hypercube outside S and does not at all vanish on the points of S. And we also are interested to find whether there is a strict separation where the polynomial cover, that is the degree of the polynomial, will be strictly less than the number of hyperplanes required.
Here results for existential or constructive.
Constructive also. So you can just give the n hyperplanes.
Sorry, here that will take any high degree polynomial and let S be the zero set of that polynomial. And that will be. That will be minimum thing, right? Minimum degree. That so that it's there is single high degree polynomial is better than product of linear polynomial.
What your polynomial to also have a lot of points on the hypercube and stuff, right?
Also, it is multilinear problem.
So Aronson et al. First studied this problem, and for forbidden set of larger size, they have given some bounds. So if we want to restrict 2 or 3 points, then they have proved that at least n-1 degree polynomial or n-1 hyperplanes will be required to cover those points. And if we restrict 4 points, then depending on the 4 points, number of hyperplanes or degree of the polynomial will change. So if for the given 4 points where we are restricting the covering, if we can give a hyperplane that will cover 3 of the restricted points, then we will require n-1 many hyperplanes to cover the points outside that 4 points. And if it is not the case, then we can do the job with fewer number, that is n-2 many hyperplanes will be sufficient.
I don't think I can.
Okay, so suppose we have 4 points, say all 0, all 1, and say the okay.
Let's say half 0, half 1, both sides. 1 on 1 0 0 0 and 0 0 1 1.
Sorry, I cannot.
I mean, I'm just giving you some suggesting some points. So you could do 0 0 0 1 1 1 and 1 1 1 0 0 0. Let's say those are the 4 points you want to exclude.
Slowly.
So okay,
But go ahead, sorry. Just go ahead.
You can use the board.
There's some chalks around.
so, can you please give me the points?
So the 4 points you were saying was 0 n,
0 to 0.
1 to the n, and you're saying 0 n by 2, 1 n by 2, and the other one. 1 n by 2 here. These are the 4 points you want to leave uncovered.
Yes. So this is where is. So suppose this is this one, is 2, is 3, and is 4. If any 3 of them can be covered with a single hyperplane, then the result says that to cover Q1 minus S, I will require n-1 many hyperplanes. Otherwise, we can do using n-2 many hyperplanes.
So, isn't it the case that you can always find a hyperplane between 3 points? I mean, there's one
No, you should, the 4th one should not be there.
So covering exactly 3
Yes.
points.
Covering here,
I see.
by definition of covering a set of points, you only cover those points.
Oh, okay.
Yes.
Okay.
If all 4 of them are on the same plane, then
But then it's easy to, since you block, isolate them and cover the rest. Something like this. Okay.
Yeah, but
It's like orthogonality argument essentially.
Okay.
Thank you.
And for any other size of S, they have given a lower bound and upper bound. So the lower bound says that if we have size, we are restricting k many points, then the lower bound will be n minus log k, and the upper bound may go exponentially large.
And these are all worst cases, that's right? Like,
Yes, the upper bound result is worst case.
yeah, is there a similar question asked, suppose if I pick the number of points, let's say uniformly random. The number is given as mod S is 4. If I pick 4 uniformly randomly points among all the 2 power n vertices, are similar results available? That number drops down order wise in some sense. Because here you allow the ability to pick those 4 values.
Yes.
I'm not allowing.
What do you mean order wise? They're all n plus some point.
So it could be log n.
But it doesn't matter, right? We've bounded on both sides by n plus.
No, that's the max is bounded, worst case is bounded.
Worst, all of this is worst case, right?
Oh, I see what you're saying.
Pick 4 uniformly
I see.
random points.
That's what you're saying.
So actually, I do not know in this result.
It's for S equals 4, nothing tells you it. Those 4 points won't lie on them. Hyperplane.
But for general case,
So, any more question from this? Okay. So,
sorry, can I ask you, so this Aronson eta is Scott Aronson, right? Is this Aronson eta, or is it a different Aronson from combinatorics, or is it the same Aronson?
children forward. Probably this is another.
Sir, the reason for asking this is, like, was there an application they had in mind while we're looking at this question? Or it was just, for its.
They just forward. And then, so there is it.
Which shows the differences.
So in this result, this upper bound, they did not give any subset for which this upper bound will be reached. But then Diamond and Fiiedi, they give construction for subsets for which will require the very high, exponentially many hyperplanes.
So can I see?
Yeah.
James Aronson.
Yeah, it's a different. This one. And this is the median curve or something?
Yes,
Arkade was on first name basis with everybody. He doesn't need.
No, because people are so curious, some people are.
Sorry, what is D sub n?
Discrete mathematics, they're all published in this. No, D sub n. They were just.
dimension in.
That is discrete mathematics.
This time I'm asking on the second line, not the first line.
So you get size of this slide.
Sorry.
From the previous slide.
Yeah, what is D sub n?
Some notation is still because there it was linear and now you're showing.
So, sorry, how large is Dn here?
No, Dn is a
Dn is some subset for which, so in dimension there exists some pattern for which the number of hyperplanes will.
It's saying that there exists some Dn for which this can be achieved.
Yes.
You require 2p omega.
Oh, I see.
But this also implies separation, the question you asked, separation between polynomials and hyperplanes, right? Because I believe if you have general polynomials, you can just write it as a Boolean function and have degree n.
I'm not able to parse it.
So there exists some subset of
Come
points.
next one.
So if you have to cover everything else, you require 2 to the omega n.
But I thought the previous thing basically said that for all points, you are like basically around n.
I don't know if there's enough monomials.
Yeah, so look at the
Last equation.
so that
Because this is k.
so you also have that plus EC to
So what can you
For just here we are restricting on only on k points.
Oh,
Yeah, this is the best way to say for every.
Okay. So it could be exponential because EC of 2 to the k comma k could actually be very large.
Yeah.
And okay.
And
But
Here-
that
yes.
question is still interesting. Now, what is the cardinality of this DN?
In fact, I would have thought the guess for DN is that you just take all things of parity 0.
No, wait, what? That's the bad guess. You just take all the odd sums.
Oh, right.
So you do interlace.
Oh, symmetric, therefore I see.
Okay, I can't take symmetric things.
Yeah.
Okay.
Yeah.
Okay.
I do find more and more.
I thought parity was ugly.
But the lower bound that they give using this size of the restricted set, depending upon the size of this restricted set, this is not tight. Because suppose we have taken these points. So for x1 equal to 1, on that hyperplane, we have to the power n minus 1 many points. Among them, we are dropping off the odd one. Instead, I am taking all 0. And this set is prime. Now I want to cover all the points outside S prime and keeping the points in S prime as unbound. Now, the size of the log of size S prime is just n minus 1. So the lower bound gives that only a linear polynomial, 1 degree polynomial or a hyperplane will be sufficient. But from here we can clearly sense that that is not possible.
The lower bound, right? What am I missing?
Yes. So I'm saying that the lower bound is not tight. So
Okay.
in this case, this gives a very trivial lower bound,
All
right?
right, okay, yeah.
Why can we sense that this is not possible?
So
Those 4 points is not.
yes,
4 points are wrong.
Those 4 points are not.
in this 3 dimension, so if I just consider the 4 points and that 4 dotted point, suppose I want to cover this 4 dotted points and I want to
It's the
keep
same.
all yes. Yeah. But only 1 degree polynomial or just single hyperplane cannot cover this 4 points. We can just prove it using combinatorial astrology or but we can just sense it. It is not possible. In higher dimension, the
So my question is what should I sense? What is the result?
so,
That's
I'm
not,
saying
that's
that
not one, the
lower
number of
bound
covering
very
hyperplanes is
trivial.
not one.
It's not 1, that is.
Yes.
Yeah.
So derived lower bound is not tight.
But how not tight is it? Is it n minus 1 versus n or is it n minus 1?
That's not clear.
So this inspires us to define a new combinatorial measure. So for a subset S which have more than 1 points, we'll define index complexity to be the smallest number R, say, for which we can get a subset of indices with size S and a point V in that set S such that every other point, if I take say some small s, then small s and V have at least one flip among those indices that are in G. So, for example, in this
Can you,
case,
so say, can you go back to the definition also?
Yeah.
Sorry.
so we have some subset of
Basis vector.
Basically, you want to separate one vertex from every other vertex using
so we have
this subset of coordinates.
yes.
So you want a subset of coordinates of size R which separate, so that for some coordinate in that set, it separates S from B, okay?
So for example,
But why would this be true? Why would there exist such a subset? Where only indices are
So this is the definition.
No.
in a set, every point,
And then you suddenly say,
if I just consider this J to be this whole N,
Yeah.
and I take just any vertex as V, then for every vertex there will be at least one field. For every other vertex.
VJ.
Oh, I see the quantification. Okay, I was
Yeah.
looking at the other way. Okay, fine. Yeah. I need to get it. It's not that for fits J, it separates it from everything.
No.
Okay, well,
Yeah.
okay.
For example, in our
There exists
case,
V and there exists J, which separates V from.
Yeah.
Yes.
For all variants.
Yeah. Yeah, that's,
so for example, if
so
I
VJ
take
is not equal to
V
the set
just
from J.
this all 0 and J to be the first coordinate 1, then all the other points have coordinate first coordinate as 1, which is not 0.
So
So
in this case, R of S equals 1.
yes,
That's what you're saying.
yes. And if we take the points which have x1 equal to 1, all these points, then this subset has index complexity exactly n minus 1.
Yeah.
And for both the cases, that is, if I just take this subset, it also has log as n minus 1, and the previous one, that is, I am dropping off all 1, instead taking all 0. This has log size same, but the index complexity for this set, it is index complexity 1, and this x1 equal to 1. This set has index complexity n minus 1, very high. And we
Can you show the definition one more time?
Yeah.
There exists a J and there exists a V. Okay, fine. So you take V equals to the origin and get 1, and otherwise, okay, got it.
that. Okay, so we can also show that this index complexity will be at most log of size of x for any subset case. And we have shown that. So if we are given any subset S of at least size 2, and we want to cover all the points outside S, keeping all the points in S as uncovered, then we will require at least n minus r degree polynomials or n minus r many hyperplanes, where r is the index complexity of the set S. And this improves the lower bound for given by Aronson et al. Since
That's not real.
and this bound is tight because for that is where we took all the points of x equal to 1 and then drop off all 1, instead take all 0. For this set, since index of is 1, so the new lower bound is n minus 1. And actually we can show that there exist n minus 1 hyperplanes which covers exactly the other points from S and no points from S is covered. Next, I go to another section. Before that, any question?
Maybe it's not, this 2 to the omega and the diamond yields are, how did they prove that development? I mean, it didn't go by the polynomial method, did it?
No, actually they.
Because the degree of the, I mean, how do you get an exponential bound?
I have not gone through the paper in very detail. So they have actually shown some pattern where they are taking half and half. So half 0, half 1, and then
It's not the polynomial.
y.
Somebody confused that the polynomial can't have degree more than n, right?
Yeah, that's what I'm saying.
So this is about the number of hyperplanes.
Yeah.
So between the lower bounds that we generally know of for the hyperplane covering typically go via the polynomial.
Oh.
This is one case where
That's
you
really not.
definitely have to.
Not a naive application of the problem.
Yeah.
Right.
There has to be something else.
Next, we will consider the forbidden sets to be symmetric. So, before going into the definition, let us first define weight of a point x. This means just the number of ones in its coordinate. And we will call a set is subset of this Qn symmetric if its points are closed under permutation. So if we have a point x from this set S and we take any other point y such that they have same number of ones in their coordinates, then we can contour that y is also in that set S. And for a symmetric set S, we define this weight of that set is to be the collection of all weights of its points.
So Q is Boolean cube, is it?
Yeah.
Yes.
Yeah. Here it goes. It's not, I was also confused.
And we define a set Tni to be a subset of first in natural numbers with 0 to be the set of where I am taking the first I numbers starting from 0 and I am taking the last I numbers starting from n. So it has 0, 1 up to I minus 1, 0, 1 up to I minus 1 and n minus 1 up to n minus I plus 1. So this set is denoted by this Tni. Venkatesh showed that if we are given any symmetric set S and I want to cover all the points from that symmetric set, keeping all the points outside that symmetric set as uncovered, then he gave a lower bound for the degree of the polynomial that is required. So it says that, okay, so here observe that when we are given a symmetric set S, we can always get a WS meaning, if the set has say some k number of different weights, then we can always get a k degree polynomial which will exactly cover that point set S and no other points outside S.
So do you want to cover S or do you want to not cover S?
For symmetric set, it is just same. So complement of a symmetric set is always symmetry.
Yeah, but the size of W will change.
Yeah, so the points, if I want to cover S, then upper bound will be of size WS.
Yeah.
The WS is what is the number of distinct weights you see?
Yeah.
Yes.
Okay.
But this result says that if S has some some Tni is a subset of Ws, that means from 0 to I minus 1, all these weights are in S and also the last I weights are also in S. And in that case, from the upper bound, instead of taking two hyperplanes, in a sense that instead of 2-degree polynomial, we can consider 1-degree polynomial and then do the same job again. So the result says that, so the lower bound for covering S, I will take all the weights and then the largest I for which the first I layers and the last I layers both are in that symmetric set S. So considering two instead of 2-degree polynomial, we can take 1-degree polynomial and then do the same job again. So this is some kind of interpretation for this lower bound. And Venkatesh also conjectured that if S is a symmetric set where both these 0, 1, n minus 1, these 4 layers are in S, and we want to cover the points of S, then the hyperplanes that will be required will be greater than this lower bound for the polynomials.
Is it the same?
No, because so suppose Tn3 is a subset of W.
Oh, I see. Okay, so even if Tn3 is a subset, it's still for any S such that Tn2 is a subset, you need WS minus 2.
Yes.
Okay.
So the conjecture was that for this set, for this case, we'll get a strict separation for polynomials and hyperplane format. But
Wait, so how will this show a separation? So this is the lower bound, right?
yes, so this is a polynomial bound, but for hyperplanes,
Yeah.
he conjectured that this will be bound. So suppose this is Tn3 is a subset of Ws.
Yeah.
Then from this lower bound, we get that Ws minus 3 will be the lower bound. Right?
It's still possible that the correct answer is Ws minus 2, right?
No. Actually, this conjecture is false.
Wait, but
So, as long as we have symmetry, we cannot get any separation between this polynomial and hyperplane. And
but no, but even the conjecture would not, even if it were true, it would not have separated the two cases, right?
sorry.
Even if the conjecture were true, it would not have separated the two cases, right?
No, it will give separation because then it will show that the hyperplane, more number of hyperplane will be required than the minimum degree of the polynomial.
You could probably come up with sets S such that the degree of P matches the inequality at the top is an equality.
Oh,
And the inequality at the
Oh, I see.
bottom thing is an equality, and then it shows the separation between hyperplane covering S by hyperplanes and covering S by hyperplanes.
so you're saying that this inequality is actually an equality. Is that the case?
Could be an equality for some sets S, right?
But the exists set says for which this is an equality.
No,
No.
inequality will be an equality. Yes. So
Okay, fine. Okay, anyway, the conjecture is not true, so. Sorry, let's go, okay.
we have shown that
Let's hope Venkatesh is not watching the video.
if the restricted set is just a single layer, that is, we want to cover all the points that have either more than k many ones or less than k many ones.
Mhm.
And I want to remain all those points as uncovered which have exactly k many ones. And for that, we have shown that we will require at least these many hyperplanes. Or the minimum degree of the polynomial will be max of this a and a minus. So, if we put n as 7 and k as 3, then we get the conjecture to be false. And this lower bound for this result comes from that index complexity framework. So we can show that for the kth layer, the index complexity is minimum of k and n minus k. And so the number of hyperplanes will be at least max of k and n minus. And the upper bound comes from this result. So this says that if we want to cover the first k layers and the last k layers, then so this 2k many layers one thing is that if I just take the xi equal to some j, where j runs from 0 to k minus 1 and n to n minus k plus 1, then this 2k degree polynomial or 2k many hyperplanes that covers all this one.
Sorry,
But-
we are taking summation xi equal to 1 to 0, 1 to all the way till k. And n minus 1, okay.
Yes. Then that 2k many hyperplanes are
Yeah.
doing that. But this says that we can just use k many hyperplanes and cover all these points in these 2k layers, and none of the other points will be covered.
What are these data happening? What is happening?
Yes. So the interesting thing is that you can take any point from this 0 to k minus 1. It will have at least n minus k many zeros.
You zero on top, so you're okay.
Sorry, n minus k plus 1 many zeros, right? Sorry,
Yeah.
ones. And here the number of ones will be at least n minus k plus.
Yeah.
So the thing is that whatever point I choose from these layers, there will be at least n minus k plus 1 many common thing. So the index of that first thing will start from n minus k plus 1, and using this we can just construct these hyperplanes.
Sorry, can you give an example? Like, for example, suppose it was just
So suppose that all 0 and all 1.
Uh-huh.
So if I just take summation xi, I runs from 1 to n minus 1 equal to n minus 1 xi.
More can
You
go.
can press the red button. The red button.
Oh. Then this single hyperplane, this covers all 0 all 1. And using this idea, we can
Hey, go back to the previous one. Yeah. So, sorry, so if you're basically removing all points that have exactly k ones in it. And you can cover them using n minus k.
and I want to cover all the other points. So kth layer is uncovered, everything else is covered.
So for suppose k was equal to n by 2. So which means that I'm just removing the middle layer. And how do I cover it using just n by 2? Oh, you use the same trick.
Yes.
Oh,
Actually, I club the first
Okay.
n by 2 and last n by 2
I see.
minus 2.
okay, I understand.
And yeah, I'm also reading the hyperplanes. And using this construction, we can also show that for any given symmetric set, the number of hyperplanes and the minimum degree polynomial, that will always match. And also, first of all, Venkatesh gave the lower bound, but we can also reach that lower bound using our index complexity.
So that was actually for
Provide to get there, but yeah.
For any symmetric set, there will be no separation between this polynomial cover and hyperplane. Now, so far we are considering the 0 1 to the hypercube 0 1 to the power n is embedded in Rn. Now we will show some result where we will consider the hypercube to be embedded in some arbitrary field. So, before going to our result, let us see some motivation behind this. So, we just saw that if we want to cover the points of the kth layer, so I want to cover all those points which are exactly k-many ones, and I will not cover any other point. If we are working in R, then just one hyperplane, this summation xi equal to k, that is sufficient. But if we consider the hypercube to be embedded in F2, then that hypercube, that hyperplane, that summation xi equal to k, here when considering in F2, this will be mod 2. This will cover every alternative layer also. But we do not want that. So I want to cover only those points which have exactly k-many k-many ones. Then how many hyperplanes will be required, or what will be the minimum degree of the polynomial?
Hey, depending on.
No, actually, so when we are considering the cube is embedded in F2, then
So k then by 2, this should be omega n, right?
at least n by 2, yes.
Yeah.
But
So
we can also
that's
say
why the
something more.
Polynomial method again now over F2.
Yes.
Yeah.
Yeah.
Hyperplane sections, like the size covered or uncovered will always be a power of 2, right?
Yeah, that's what I was wondering, is it even
Power
possible?
of 2 to the n. If you take a hyperplane, it'll cover half the points. You take another hyperplane, it'll either cover half the remaining points or nothing at all. So, if you take a system of hyperplanes, the value of zeros will always be a power of 2.
Or here, instead of hyperplanes, suppose we are just interested in finding polynomials. So, what will be the minimum degree of the polynomial? So, one thing is that when we are considering in F2, so
look at polynomial cover.
yes.
So this point is 2. Right?
I mean, if you have a set of, if you have any set of 3 points, for instance, you can never cover it exactly using hyperplanes.
Yeah, that's very powerful.
Yeah.
So, when we are in F2, uncovered means at those points, the value of the polynomial is just 1. And zeros are just 0. So, if we take some other polynomial g, which vanishes everywhere except the kth layer, and then define p to be just 1 minus that g, then p has the same degree as g and it just flips. So, in F2, instead of starting the question of the minimum degree polynomial which vanishes exactly at kth layer, it is equivalent to studying the minimum degree of the polynomial which vanishes everywhere except the kth layer. And we have proved a more general result. So, suppose f is any arbitrary field, finite or infinite, and this 0, 1 to the power n is embedded in Fn. And G is a polynomial where coefficients come from that field F, and it covers all the points except in the kth layer. Then degree of G will be again from k and n minus. So previously we saw the same result in R, but that result is just not true in R. In any arbitrary field, the lower bound remains the same.
Is there an upper bound or is this shadow?
Yes. So actually, in F2, there are infinitely many n's and k's for which that n minus k, or I mean,
That's also another one.
yes,
But the trick instead of one minus this thing, that
yes,
won't work if you are in an arbitrary field, right?
yes.
So you have to do something else.
No, so, the,
Against the x power t minus one.
yes,
Huh?
so here,
No,
that,
but that field is very large, going to that.
Single degree is different.
I think,
But finite field it will
No,
work.
I think she is
No, the
just
one
connecting
minus was
the
just
two
to move
problems.
from covering QK to covering all but QK.
Yeah, but.
The next statement is a statement about any field.
any field,
You are working with covering all but QK.
Yeah,
yes,
Oh, it's only all but few.
yeah.
Yes.
Then it.
yes. And
This transformation is
Yeah, the
not.
transformation requires.
It's just to connect the two seconds.
And so from this result, as a corollary in F2, we get that to cover a single layer, this will be again the lower bound.
Yeah.
So this says that in F2, if we just want to cover,
By the way, the F2 is a known result.
Oh.
The exact threshold functions have that degree. Very well, classical result.
so in this is already known.
Over F2, I don't know what.
Over F2?
Yeah.
Any K?
Yeah.
Okay. So, and the tightness is,
Ninth time,
and the
90s,
tightness is also known.
yes.
Oh, okay.
The polynomial question, the hyperplane.
No, actually,
This is
so
all for
I did not know that.
So can you show the example?
So, I have taken, so for, suppose n is even, and I am considering k to be the n minus one, that is, I want the polynomial to be non-vanishing exactly at n minus one and vanishing at all the other layers. And then we can take this as product of n minus one many variables and their sum. So this is the n minus one degree polynomial, and in F2 this answer. So next I will come to covering with multiplicities. So suppose we get back to the original problem by Alon and Fiiedi. So the hypercube is again embedded in Rh, and we keep the all zero as uncovered, and we cover all the other vertices. So observe that if I just take this xi equal to 1, these hyperplanes, then all the points except which have exactly one weight, then only these points are covered once, all the other points is covered at least once. And all these points that are covered exactly once, I can just add this hyperplane summation xi equal to 1, and then all the points are covered at least once, and this all zero is again uncovered. So the question is that if we are given two natural numbers L and T, where L is the smaller one, and a subset S of Qn, then we want to cover all the points outside S T times, and every point in S exactly L times. Then what will be the minimum degree of the polynomial, or what will be the minimum number of hyperplanes required?
Are we allowed to use the same hyperplane multiple times?
Yeah. And zero, so for polynomial, so hyperplane, we know how many hyperplanes are covered. So for polynomials, this multiplicity is just, we'll consider V has multiplicity T if it itself was zero, and all the derivatives up to order T minus 1 also vanishes. And Clifton and Wang, they first considered this T0 covariant. And and they considered the hyperplane version. They showed that if we want to cover all the vertices except all 0 using hyperplanes and cover everything at least 2 times, then at least in plus 1 many hyperplanes are required. If we want to cover every non-zero point at least 3 times, then we will require at least n plus 3 many hyperplanes. And both these are type, that is, there exist n plus 1 many hyperplanes that do their job, n plus 3 many hyperplanes that do their exact job. And for higher values of n and t, so the dimension is higher and t is also the number of how many times we are covering, that is also greater than 3. For that, they have given this lower bound as n plus t plus 1 and upper bound as n plus t choose 2. So there is a huge gap between this lower bound and upper bound. And so Clifton and Huang considered this T0 covariant for hyperplanes. So again we can ask the same question for polynomials. And Sauerman and Wigderson, they studied this T0 polynomial covariant. And they have shown that if n is sufficiently large than t and we want a polynomial that covers all the non-zero points at least t times and does not vanish at the origin, then the degree of the polynomial is at least n plus 2t minus 3 and that bound is tied up. That is, there exists a polynomial of degree n plus 2t minus 3 which vanishes at every non-zero point at least t times and does not vanish at that origin. So first of all, this
No. I was just going to tell Arkadev that it's Yuval big person. Yeah, Arkadev knew that.
Very surprised because I think.
and so first of all, this gives a better lower bound for that hyperplane cover that Clifton and Huang considered. But still, it cannot guarantee that for the hyperplane space, what will be the any data construction is there. So this suggests that there might be a separation for this polynomial covariant hyperplane cover when we consider with multiplicity. But still, we do not have any proof that this polynomial lower bound will not be sufficient for hyperplane. So we have shown a separation for this polynomial and hyperplane cover. So suppose T is
Sorry, the 2 to the omega n of Yehuda, why doesn't that achieve this already? Because isn't it true that?
There's
so,
no
so the
multiplicity.
lower bound
Oh, good multiplicity. Sorry. Go ahead.
so suppose T is any number greater than or equal to 2 and P is between 0 to n, an integer, such that it satisfies this condition. That means, so P and n minus P, minimum of that is sufficiently large than T. And S is any symmetric set such that it consists of all the points in the first periods. So weights are from 0 to p minus. And we want a T0 covering for this set is, that is all the points which have weight less than P, that will be covered at least T times, and the points which have weight at least P will be uncovered. Then what will be the minimum degree of the polynomial? So we have shown that this will be minimum of P n minus P plus P minus T. And also we can prove this directly. And this gives a strict separation, because if we take any n which is at least 3 and P to be just 2, then at 2, 0 hyperplane cover. So from this lower bound we will get this at least 3 hyperplanes will be equal. But we can actually show that no 3 hyperplanes can cover the 0th layer and first layer at least once, while covering while keeping all the other points as uncovered. So there is a strict separation even for symmetric sets when we are considering with multiple sets. Quick recap. So for any given symmetric set, when we are covering, when we are considering that covering and uncovering thing, then there is no separation between the polynomial cover and hyperplane cover. But when we are considering with multiplicities, then there is a strict separation even for symmetric sets for hyperplane cover and polynomial cover. And for any given symmetric set, if we want to find what will be the minimum degree of the polynomial or even the number of hyperplanes, that will be a T0 cover. That is still unknown. So for restricted set is when it has size just 1, then we have the result by Lisa Sauermann-Wigderson for covering with multiplicity, and for covering with hyperplanes we have results for by Clifton and Huang. But when this restricted set has larger cardinality, then the result is still open.
The T comma A is somehow reduced to T comma B.
Yeah.
I want so I wanted to rather than multiplicity T everywhere and multiplicity 5 everywhere.
They have shown that for T minus 1 covering, there will be the lower bound will be n plus T minus 2, and for all of the L starting from 0 to T minus 2, the lower bound will be same.
More questions? So, sorry, I'm still thinking about the diagrams. So these, have you looked at covering all the ones of inner product model? That seems like the should be very hard, right?
So,
It's an abundant person.
Yeah. That would be like terribly hard,
So
right?
you have two n variables, x1, and I mean, there are two n things, but let's call it x1 through xn and y1 through yn, just for simplicity. And you take all those 0, 1 values such that summation xi yi is 1 constant.
It's like parity, but you replace each thing by a simple X or Y. You know. This should be, this should be.
Yeah, if anything, we should.
This should be.
I think, yes, their same is also very.
This is, I would think so.
More questions? Let's start again.